Example 7.9, show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. According to the question, show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. First of all, take one single particle. This is our single particle and it is moving with some velocity, that is linear velocity, constant velocity, that is v, and its momentum is also in the same direction, p. Okay, according to the question, so this particle is moving with the constant velocity. Constant velocity means it is not changing the direction. Okay, somewhere it is started here and it is moving in a straight line path, for suppose. Then observe this particle from any point. Okay, so this is our any point. From that object, from that point, we are observing this particle's motion, that is angular momentum. Okay, so the position vector of this particle from that point, any point, this is nothing but here position vector r. Then if it is the r position vector, okay, this is our position vector and it is our velocity vector, and angle between them is if it is theta, then according to the angular momentum, that is L is equal to, for a single particle, L is equal to r cross p. This is the formula for angular momentum of a single particle. So if we write about this point we consider here O. So about this point here, this is the particle. On this particle, the momentum of the particle is p, and position vector is r, and angle between r and p, okay, that is equal to theta, and it is also angle between r and v also, but we have to consider here we require here p and r, so that's why the angle between r and p is theta when we are observing from the uh, uh, arbitrary point O, and when the particle is at here, for suppose it is we are taking here point A, then this particle is moving with constant velocity, and after sometimes it is moving another place. Okay, before that, so the angular momentum L is equal to, when particle is at A, that is r cross p. Okay, and that is equal to rp sine theta. According to the cross product, if we are removing this cross product, this is equal to rp sine theta. It is magnitude of the magnitude of the this what angular momentum, that is rp sine theta. Okay, so then this is also we can write, that is r sorry, this is equal to p r sine theta. P and r sine theta, this L is equal to, okay, so P is the linear momentum P, and r sine theta is the perpendicular distance, it is theta, means this is also how much, opposite angles are same, that is theta. Then this distance is nothing but here it is I am taking here m. Okay, then this OM, it is opposite side according to our sine theta. What is the sine theta? Sine theta is equal to opposite side by hypotenuse. Opposite to this theta is OM. So this is OM by hypotenuse is this one. Okay, this is 90 degrees. So this magnitude of R is nothing but here vector R. Okay, This is OM by R. From that, OM is equal to R sine theta. It is the perpendicular distance. This is R sine theta is perpendicular distance. Then this particle is now moving. It is moving with constant velocity. Constant velocity means the magnitude and direction will not change. Okay, when this particle is changing to another position, that is B, and which is moving in the same straight line path, and again we are observing from the same arbitrary point of this particle when it is at B, and the position vector is here vector R. Then this position vector is makes an angle with the P vector, that is again it is theta. Then this it is opposite side theta, and then this perpendicular distance is R sine theta. So L is again it is equal to L is equal to, that is P, and this is R sine theta, and that is equal to P is equal to MVR sine theta. Okay, so its magnitude is constant, and as well as direction is also constant, because here this is R. Okay, so this is R and it is our P, R and P. Okay, like this into the plane. Okay, and this is R. Okay, this is the position vector R, and again it is our P. So R and P, so direction and magnitude both are same. So when a particle moving with constant velocity, from when it is moving with a constant velocity, if we observe from the one axis, one arbitrary point, then its linear, sorry, its angular momentum is not changing.